can now model, every player's shot chart can now be modeled as a linear combination of 10 numbers, right? So you can now we can model every player not using a 2,000 dimensional model, right? But now a 10-dimensional model for every player, right? And it's non-negative, so it's just a non-negative linear combination of these, and this is what this looks like. The training data is from provided stat sports view, which actually provides the XY locations and where people shoot, where people had the ball and chose not to shoot, stuff like that. That's how we estimated the model. Looks like this. We learned this probabilistic model of actions like shoot, pass, and stuff like that. It's a logistic regression model actually that we trained on. So there's some scoring function that scores the affinity of the player, you know, let's say in the simplest case, shooting or not shooting, given the game state, right? And so this scoring function, F, is actually this guy, which is actually a range factor model.
Does he go free throws?
This is just static shots. This is the most simplest version of the game representation. So we literally just minimize the log loss of this model, subject to regularization. Here we're actually regularizing over, here actually this is a little bit incorrect. We're regularizing over VNL. Oh, there we go. And so just apply chain rule. So now it's like log loss with a link factor model. So you just apply, instead of squared loss, so you just apply chain rule, and then you get the same type of alternating optimization. So we can do things beyond just passing, shooting. We can do, say, where do players like to receive passes? And again, most players haven't played that much, so we could again take a lane factor modeling approach. And so these are the 10 factors, so k equals 10 here, of archetypes of common places where players like to receive passes, and here's a linear, these players that just represents a linear combination for these. Yeah?
Did you just cross-validate to find the number of like looking factors?
No, actually for this particular, so that's a good point. So for this particular case, I chose k by visual cross-validation. You could also choose k by accuracy. So I think the most accurate k was like 12 or 13 or something, a little bit more than 10, but I like the visualization of 10 better. So here, where do passes tend to flow? So if this is the locations on the court. So if you are over here, you tend to pass to someone over here. If you're over here, you tend to pass to someone over here, and so on and so forth. If you're interested in the details, they're all in this paper on my website. And then you could actually visualize this F matrix. If you're at this location, where are you more likely to pass to? So this is just a row. This is just visualizing a row of this matrix. If you are here, where you're likely to receive a pass from? No, pass. Yeah, if you're passing to there, where is the ball handler likely to be? This is visualizing a column of this F matrix. Again, this is all non-negative matrix factorization.
Do you simplify the model too much because you only consider one player here?
Yeah, probably. I mean, certainly not probably. Yes, definitely. We absolutely simplify the model a lot. But, in some sense, this is a much richer model than what people have done in the past. Yeah.
Is there like an intended application for this?
I just wanted to visualize things. Yeah, I mean, I've demoed this to some NBA teams and some sports analytics startups, but my original interest was I wanted to see if I could see cool patterns from the data. That seems like a very childish answer, I know, but that's one of the joys of being able to do research. Yeah. It did inspire some research questions later, but in the beginning it was just a sort of a data visualization and exploration.
You're still pursuing research questions like
yes. So right now we are looking at modeling dynamics. We're looking at trying to do speed up optimization. So these models take a long time to train. How do you speed up optimization? How do you do dynamics? So these are still frames, right? They don't model dynamics. Offense and defense, something that you can else to model? There's many things you can model. This is just the most basic stuff you can do. Yeah. Okay, so for the final few minutes, I want to just, actually final like 1 minute, talk about tensor latent factor models. So tensors are a higher order generalization of matrices. So this is a 3 tensor. So a matrix is a 2 tensor. Right? What does that mean? It just means it's so if a matrix is a 2-dimensional array, a 3 tensors is a 3-dimensional array, if you were to sort of implement this as a data structure. Right? So, and then one could do tensor factorization. So assume that this tensor can be factorized into the product of 3 low-rank matrices, low-rank matrices. Right? So why might this be useful? Let's see here. All right here. So for example, instead of having users and items, right? Imagine we're doing personalized search engines, right? So if you issue a query to a search engine, I want to compute the match of that query to a search result, right? But I also want to personalize this search result to things that I know about the user, right? So Google has a personalized search option, and they certainly personalize to geolocations just by default right now. And so you can imagine a 3-way model, right, where you model both some things you know about the user, things you know about the item, the search result, and things you know about the query, right? So now it's a 3-way interaction model. It's a trilinear model. And again, this can be an incredibly large model parameter space. And we can make the same low-rank assumption that it factorizes into 3 relatively low-rank matrices. And this is just a 3-way dot product, also known as which you can model using the Hadamard product. It's related to the Hadamard product. And you can actually solve something like this using gradient descent. Right? The same principles of alternating gradient descent, holding these parameters, holding two sets of parameters fixed and computing the gradient for the third. It works for 3-way models too. You just sort of rotate. So nothing changes there. And if you have enough data, you can estimate this model fairly reliably. Okay, so just to summarize the latent factor models, the whole premise of latent factor models is to learn a low-rank model of a matrix of observations or a tensor of observations, right? And the reason why it's a matrix of observations is because the dimensions of the observations can have some notion of semantic meaning. One can interpret this using as sort of multitask prediction. One can interpret this as trying to fill in missing values. We can also use features, right? So these U and Vs can be multiplied by features. And this type of approach is widely used in industry because this low-rank assumption not only gives you tremendous statistical efficiency because the number of parameters you can estimate is significantly less than trying to estimate like a full matrix of parameters, but furthermore, it seems to be valid in many applications. In many applications, it seems like the variability of whatever it is you're trying to model behaves according to a low-rank manifold, low-dimensional manifold. And this is sort of the simplest case, which is a linear low-rank manifold. Any questions? Okay, so next week we'll be looking at embeddings and deep learning. Recitation next Thursday on advanced optimization techniques. That's it. No homework due next week. Yeah.
This is a good comment.